All right, we're going to talk about counting and how to get those values. Multiplication counting rule. Okay, for a sequence of events in which the first event can occur in n sub 1 ways, the second event can occur in n sub 2 ways, the third event can occur in n sub 3 ways, and so on. The total number of outcomes is n sub 1 times n sub 2 times n sub 3 times ... how many you have. Okay, kind of an example of this is like if you go to dinner and you have an appetizer, you have 3 choices for appetizer, you have 4 main dishes and 2 desserts. How many different ways could you have a meal? You would go 3 times 4 times 2, or 3 times 4 is 12, times 2 is 24. So there's 24 different ways you could have that meal. Okay, multiplication counting rule, the hacker guessing a passcode. So when making random guesses for an unknown 4-digit passcode, each digit can be 0 through 9. What is the total number of different possible passcodes, given that all the guesses have the same chance of being correct? What is the probability of guessing correct on the first attempt? Okay, so the first thing we need to do is find out how many different passcodes there are. Well, we look at this. Well, how many numbers are there? There are 4 numbers. Well, in the first case, we could have 0 through 9. So there are 10 different possibilities for each digit. So the total number of different passcodes is n sub 1 times n sub 2 times n sub 3 times n sub 4. And they both have 10 possible outcomes, or there are 10,000 different possible values there. Okay? So understand that in a 4-digit code, there are 10,000 possibilities as long as every digit is accessible, right? If we went to 5, this would be 100,000, so on and so forth. Now, what is the probability of guessing it correct on the first attempt? Well, if I go to guess it, I only have one guess, and there's 10,000 outcome, so the likelihood is 1 in 10,000, or 1 10,000th. Okay? Factorial rule. The factorial symbol, which is this exclamation point, denotes a product of decreasing positive whole numbers. For example, 4 factorial is 4 times 3 times 2 times 1, which equals 24. By special definition, 0 factorial is always 1. Okay? Factorial rule. The number of different arrangement orders matters of n different items when all n of them are selected as n factorial. So if I said, hey, I have 10 books, I'm going to read, what can I read them without rereading them? So, for example, you have 10 selected in the first read. Once you read it, it's gone. Now you have 9, 8, 7, 6, 5, 4, 3, 2, 1. You'd multiply those all together. Example 2, the factorial rule, travel itinerary. Statistics researcher must personally visit the presidents of the Gallup, the Nielsen, Harris, Pew, and Zogby polling companies. How many different travel itineraries are possible? Okay, so the first thing is we look at this. Well, how many choices does he have going to someplace first? Okay, so he has 5. So there are 5 different presidents. The number of different travel itineraries is 5 factorial, or 5 times 4 times 3 times 2 times 1, or 120 different possible routes that he can take. Okay. Second question, if the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest? Okay. So there's only one itinerary with the presidents visited in order of age. So the probability is 1 to 120, right? So these are in order of age. So there's only one possible outcome, so 1 in 120. Permutations and combinations. Permutations of an item are arranged in which different sequences of the same items are counted separately. The letter arrangements ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. In permutation, order matters. Combination. Combinations of items are arrangements in which different sequences of the same items are counted as being the same. The letter arrangement of ABC, ACB, BAC, CBA, CAB, and CDA are all considered to be the same combination. Order doesn't matter. Okay? So these are like, combinations are like committees. It doesn't matter when you got selected, you got selected. Okay? Permutations are items, are arrangements in which different sequences of the same items are counted separately. So this is order, right? So this is like president, vice president, secretary, treasurer. Order matters in how they got selected. Permutation rule. So when n different items are available and R of them are selected, without replacement, the number of different permutation order counts is given by this formula. NPR equals n factorial over n minus r quantity factorial. Okay. The nice thing is this is built into your scientific calculators, so it should be pretty quick. Permutation rule with different items, the trifecta bet. In a horse race, a trifecta bet is won by correctly selecting the horses that finish first, second, and third. And you must select them in the correct order. The 140th running of the Kentucky Derby had a field of 19 horses. How many different trifecta bets are possible? Okay, so now I have 19 horses, that's my N. I'm going to select 3 of them. Okay, so there are 19 horses available, and we must select 3 without replacement, right? You can't have the first horse win, second and third. The number of different sequences is going to be 19 permutations of 3. Okay, 19 permutations 3, so this is going to be 19, this is going to be 3. So it's 19 factorial over 19 minus 3 factorial, or 5,814. Now, if I wanted the probability that you will, with 1 ticket purchase, win that, it would be 1 in 5,814. Permutation rule when some items are identical. Okay? So the number of different permutation order counts when n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows. So n factorial over n sub 1 factorial times n sub 2 factorial times ... all the way to n sub k factorial, where n sub 1 are like, n sub 2 are like, and n sub k are like. Okay? So we're going to kind of look at this permutations rule with some identical items. Okay? So kind of go back here. This is what this is saying is, if I had, let's just use the word book. Okay? And I said I want to know all the possible outcomes of the letters book. So that would be 4 factorial over, and I'm using all the letters, right? Over 2 factorial because I have 2 O's here, okay? So that would give me 4 times 3 times 2 times 1 over 2 times 1, which would give me 12 different possibilities, right? Because I don't know if I'm going to make this sub 1, sub 2. This, when I look at it, I can't tell the difference, right? Unless I put those subscripts in there. And that's what we're talking about. So those are identical values there, but I wouldn't be able to tell unless I added something to it. And so we want to make sure that we have that piece of information. So when designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used? So we have 10 questions with 2 that are identical to each other and 3 others that are also identical to each other. So we're going to use that formula for identical. So we're going to have 10 factorial over 2 factorial times 3 factorial, which will give us 302,400. Okay? So, combination rule. when n different items are available, but only r of them are selected without replacement, the number of different combinations, remember, order does not matter, is found as follows. N choose r equals n factorial over n minus r, quantity factorial times r factorial. Okay? So in California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers, 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order does not make a difference. Okay? So how many different lottery tickets are possible? Well, that would be a combination of 39 different items chosen with 5 of them. So we have 39 choose 5 or 39 C 5. So we have 39 factorial over 39 minus 5 factorial times 5 factorial, which is 39 factorial over 34 factorial times 5 factorial, or 575,757 different possible tickets. Find the probability of winning the jackpot when one ticket is purchased. Well, when only one ticket is purchased, we have a 1 in 575,757 chance. Permutations, combinations, officials, and committees. The Google company must appoint 3 corporate officers: Chief Executive Officer, CEO, the Executive Chairperson, and the Chief Operating Officer, COO. It also must appoint a planning committee. So how many different ways can the officers be appointed? Well, is choosing an executive officer and then somebody else as the chairperson and somebody else as the operating officer different than if I flip those people around? Yes. So we're going to use permutation because order counts. So permutation of r, so we have n equals 8, r equals 3, so we have 8 factorial over 8 minus 3 factorial, or 336 different ways that 8 people can be selected to be these 3 officers. Now, if I want a committee, how many different ways can the committee be appointed? Order does not matter. So we want the number of combinations of r equals 3 and 8 equals 8. So this would be 8 factorial over 8 minus 3 factorial times 3 factorial, or 56. There are 56 different ways that a committee can be selected. Okay? So that's kind of getting you guys understanding counting principles and how do we find the total number.